So continuing our discussion of different components that are in the hydraulic systems, I bring charging valves up because these are used to charge the accumulators with nitrogen. And I brought a couple of them because I want to be able to kind of show you how these work. They're a little bit, it's a little confusing to try to explain it, I guess. So, but they're used for, it's underneath the cap there. You can see the cap looks similar to what you would have on a tire. It is a Schrader valve, but it's a modified Schrader valve. And we put nitrogen in typically around 1/3 to 1/2 the system pressure. But a few things there, we need to make sure when we're checking our accumulators that the fluid is fully bled out of them. So like we had brake accumulators on the planes, before we would check the accumulators, we'd go up in the cockpit and pump the brakes a bunch of times. Or like the 727, if you're working the air stairs, you would want to drive the air stairs up and down a couple times to make sure all the fluid is pushed out of the accumulator. And that way it's just nitrogen that's in there. That piston is either fully to the bottom or fully to the one end, or the balloon is fully inflated, push all the fluid out. And when you do that, then you fill it to that. Because if the system's pressurized, it's going to compress that fluid and it's going to compress that nitrogen or that air, and it's going to match whatever pressure the fluid's under in there. And so it's got to be fully empty. We would have this where people would service these. They wouldn't make sure that ours were piston accumulators. They wouldn't make sure the piston was all the way over. They wouldn't have pumped the brakes. They'd service them. And then the next time someone pumped the brakes down, the pressure would be low because there would be more space in the accumulator. And we'd find them low quite often because of that. So I've got a couple of them here, and I'm going to just show one. Next thing I've got hydraulic heat exchangers. And we mentioned that these are typically installed downstream of the pump case drain. So here's our pump. And we've got our case drain line. There's a filter for the case drain, and then it goes through the heat exchanger and back to the return side. We've got our engine-driven pump over here. Case drain comes off the right side, goes through a filter, check valve, comes in. So you can see both sides in this case come through a single heat exchanger, but they have separate case drain filters. That's pretty normal design. And most of them, the most common you're going to see out there are fuel and oil type. And that is, we use the cold fuel as our heat sink, as our area to send the heat that's built up. So cools the hydraulic fluid, provides a little heat to the fuel. In all honesty, these are running through oftentimes the wings. The wings are such large tanks of very cold liquid that the heat they add is negligible. They really aren't going to prevent icing in the fuel or anything like that. That's what the fuel heaters are for down on the engines. But they sometimes can be located on the engines where it's a fuel line, like what you've seen. Those of you that have seen the one on the JT9, that's not for cooling these hydraulic pumps, but it's a similar type of design. Or they can be air oil. There are some cases where the heat exchanger, instead of having fuel run over the other side of it, has air go over the other side of it. So the CRJ 200, I worked on the left and right system, or the number one and number two system. They had fuel cooled heat exchangers in the wings for each system. And then the number 3 system, which was the central system, it had an air cooled heat exchanger back in the tail area, where the same air that was used for like cabin cooling and that kind of thing, a portion of that was brought over the heat exchanger to cool the hydraulic fluid. And that one had a fan that on the ground, you'd hear that fan kick on. If you were running hydraulics, that fan would cycle on and off while they were running. So typically located in engines, airframe, equipment bays, that kind of thing, and they would have a ground fan to provide airflow on the ground if you're running these. Construction of them, 3 main types: tube, shell and tube, and then your air-cooled. So tube type are just that. They take a bunch of hydraulic tubing, hydraulic line, rigid hydraulic line, and they're located inside of the fuel tank. This is the bottom of, you can see the wing structure here, bottom of a wet wing style fuel tank. So where the inside of there's no bladders or anything inside of these. It's just the The wing structure itself is sealed and the fuel's inside the wing. And the fuel's used as your heat sink. They're held by various clamps and standoffs kind of near the bottom. They're at the bottom of the tank, so they're submerged no matter what the fuel level is. They're typically at the very inboard near the root of the wing, which also is the lowest, kind of puts them in the lowest part of the tank. And as the fluid travels through this kind of coil, these coils of tubes with the fuel around them, it's going to cool that hydraulic fluid off. So a shell and tube style gets its name from the fact that it's got an outer shell, kind of looks like a big pipe. And then inside there are tubes that run from one end to the other. So on this diagram here, you can see there's a port on the far left and a port on the far right that are on the end cap. That would be the tube outlet and tube inlet shown in the diagram. And then in the end here, then you've got what's called the shell area, and that's those two ports sticking straight up. And in the shell area, you run your fuel or whatever's going to cool it. So the oil would go in this tube inlet, travel through these tubes that run from one side to the other, and then out the outlet, and then the fuel would come into the shell inlet here. And you can see there are baffles in here that kind of force, it doesn't just come in and go straight across, it's kind of got to flow back and forth across those tubes a little bit. And that provides that cooling, that heat exchange to take the heat out of the hydraulic fluid. I also put oil there. This is the same way a fuel oil heater or an oil cooler on like an engine would work as well. Okay, so you see one of these, when you do fuel on the JT9 in the engines class, you'll see one of these installed on the JT9 when you do your fuel lab. And then air cooled looks like you've probably all seen radiators and that kind of thing. So the hydraulic oil, you've got an inlet and an outlet. It's going to travel through these kind of flat tubes. It goes from the top to the bottom or the bottom to the top in the right side and then out the other end. And then all these fins in the middle increase surface area and heat transfer. So then air gets pumped through here, typically by a fan on the ground or by ram air and fight, and removes heat from the system. So our three coolers, again, almost always found downstream of the pumps in the case drain side of the system. What's that? The majority of the heat that builds in the system is in the pumps. And so the case drain, that fluid that's not sent out the pressure side, it's flowing through the case in order to provide lubrication as well as carry heat away from the pumps. And so that's why it makes the most sense to have the heat exchangers in that area, because that's where your warmest fluid is going to be after. So you've got fluid goes from the reservoir to the pump on the suction side or the supply side. And then the flow from the pump, you've got your pressure fluid that goes out to the system. And then you've got your case drain fluid that's provided lubrication, as well as picked up heat being generated in the pump. That goes out to the heat exchanger before going back to the reservoir. We have several different types of valves. We've got to control our system, and we've got to control there's two things we look at. We have flow and pressure, right? We want to maintain a certain pressure in the system. And what's the most common pressure? 3,000 PSI, okay? And then we also have to control flow. Flow is to turn things on and off, in simplest form. But sometimes we also have to be able to control rate of flow or direction of flow or sequencing of flow from one component to another. So you've probably heard of sequence valves and priority valves and that kind of thing. And we'll look at those. So here's a bunch of different types of valves for flow control. So simplest ones are check valves and snubber or orifice check valves. We've got various selector valves, sequencing, priority. Flow equalization, hydraulic fuses are a form of valve. And then pressure control regulators. So simplest valves we have are check valves, and these are operated by the hydraulic fluid flow itself. So here's a simple check valve. In this case, at the top, a ball type check valve. Fluid can flow from the left to the right. It's going to push this ball off of, there's a seat right here, flow around the ball and out to the right. But if then the spring, if fluid flow is shut off, or if the fluid tries to go from right to left, that spring pushes that ball back against the seat and blocks any flow of fluid from right to left. Okay. A variation on these, same, but right below that, cone type works the same way. Fluid pushes on the cone from the left, pushes it off these seats right here, and then is able to flow, and there's an opening in the cone on the downstream side of the seat to go this way, but then it's going to prevent fluid from going right to the left. And then below that at the bottom is a flapper valve. These are essentially little spring-loaded doors. They can, they're hinged here. They can flip up and down to allow fluid to go left to right. But if fluid tries to go right to left, the doors shut and prevent it from going back that way. With any of these, we can create a modified version of them to create something called a snubber valve or an orifice check valve. And these allow relatively free flow of fluid in one direction, just like the check valves. There is going to be a small amount of resistance there, right? A certain amount of force is going to be required to push this valve open, or the cone over, push the ball over, push the doors open. But it's minimal compared to the amount of blockage it has going in the reverse direction. An orifice check valve, you can see they've created kind of a little bypass right here. On the bottom below the seat. And so fluid can flow much more freely to the right, but then when it goes to the left, the majority of the flow path is blocked, but a small amount will still be able to go through that bypass, that orifice passage right there. Okay. The same kind of thing can be built with like a cone type check valve where they drill a small hole in the very tip of the cone, right? So one way it can push the cone over and get a lot more flow through multiple holes. But when it goes from right to left, it would only be able to go through a small hole that's in the tip of the cone. Same thing with these doors. You put a small hole in the doors themselves. Fluid can flow freely from left to right. If it tries to go back from right to left, then it would go through a small hole drilled in the door rather than around. Or they create some kind of a bypass passage like the orifice passage you've got going here. Selector valves are kind of our next when we're getting in complication and use. Another very common thing, selector valves are going to direct our flow of fluid. And these, we may need to go to a specific direction or specific component. We want to be able to operate something, and they can be either rotary style or spool style are the two most common. And honestly, majority of them that you're going to see on transport aircraft are going to be of the spool style. But there are some rotary ones out there. They can be operated all manner of ways. So manual operation, is probably the easiest, simplest. However, you're not going to run back to the tail every time you need to actuate a valve to move the elevator, for instance. So manual is not always possible. Some of them are spring operated. Various things can push on them. Mechanically operated, something pushes against the valve, causes it to move. But by far, the ones you're going to see most often are solenoid and pressure-operated valves because those are remotely controlled. Solenoid is an electric motor or an electric torque motor type setup. And then pressure or pilot valves is we use the pressure in the system itself. We take a small amount of that pressure and we use it to drive an actuator. But the flow to that actuator has to be controlled by a smaller. Typically, a larger valve is moved by pressure. That pressure comes from a solenoid valve porting fluid to the actuator. And so they're kind of piggybacked on top of each other. But rotary valves look something like this. So remember, these are closed center systems. So here's our pressure manifold in kind of the orangey color. Blue is the return. And this shows right now in a gear, I guess it would be in a retract scenario. So pressure coming from the pressure side, going to the right side of this actuator. It's going to push the cylinder, the actuator to the left. And the left side is being ported, allowed to go to the return. So you can see this valve can be rotated in roughly 3 different orientations. One ports fluid pressure to the right, return on the left. The other one's going to port fluid pressure to the left, return on the right. And then the third one is neutral. With a closed center system, we need to be able to block off all those flow paths when we're not actually sending fluid there. So they're able to put into a fully closed position. Spool type valves get their name from the fact that they look like a spool of thread. Okay, you can see a simple single one. Now these can be ganged on top of each other. You can have more than one spool in a given valve, right? You can have this spool, and then you could have another section, another section, another section, where that valve can actually actuate multiple things and multiple points of travel. But simplest design, kind of shown there on the left, is, we've got this valve, top left corner is pushed to the right now. It's compressing a spring. So that's going to port fluid. You can see the red ports that are connected together, right? If you release that valve, you let go of it, it blocks off the red and it ports the fluid to the left side now, or it kind of acts as a return. Below, you can see kind of a different method of doing this, right? When it's pushed, now it's porting fluid to the blue side. And when it's released, it'll port fluid to the right. These symbols here are kind of the industrial symbols you'll see for valves. If you look at like a drawing, it kind of shows how the fluid can flow. But the one on the right is kind of that dual, that dual ability. We want to be able to control both pressure and return simultaneously. And so you can see this is the same valve in two different positions. The left of the two positions, you can see pressure is going around the outside of the spool and down to the right side of the cylinder there. The return is ported, and in this case, there's a hole drilled through the spool from end to end. So you can kind of think of that, if you have a spool of thread, it's got the hole down the middle of it, right? So that allows fluid to return from the left side of the actuator. It goes through that hole in the middle and up the right to the return. If we push this valve over, now the pressure is able to just go past the end of the valve to the left side of the cylinder. The return fluid goes up and goes around the center of the spool and out the return. And we're no longer using, nothing's happening with that center hole port in that position. So again, there can be multiple of these. If you look in like a landing gear actuator or landing gear valves or flight control valves, you'll see these spool valves. When you look at these, it'll be spool, spool, spool. There'll be another central piece with a spool end, another central piece with spool end. They'll be all piggybacked off one another, and they provide sequencing and control scenarios. Okay. So there's a video that you're welcome to look at on kind of your own time here, but it just kind of shows how those move. When we put these into systems, they'll get names based on what they control and how they can control it. So basic mechanical valves, sequence and priority valves, are going to control one item at a time. They're types of other valves. They might be a spool valve, they might be a check valve, they might be a selector valve of some kind. But here we have sequencing valves that, in this case, it's showing a very simple system. Gear doors need to open before the gear goes down. And so when we've put pressure on our valve, you can see pressure flows and it goes to the door open side of this actuator. The return side of the actuator is able to flow. It goes down to the sequence valve. It works as a check valve right now, and that allows it to go to the return side. Okay, but you can see here, this left sequence valve acts like a check valve. And initially, pressure isn't going to be able to flow past it. It's going to be blocked by that bead being against the seat until the point where the gear doors reach their fully open position and they press this little T, and that pushes the valve off the seat, and then it'll allow the gear, in this case the actuator pushing up, moves the gear into the down position. So that way the gear doors open first, and then the gear drops down. If you look at it from the reverse scenario, if we were to turn our valve and we port fluid, right, it's going to freely send pressure to bring the gear up. And once the gear gets all the way up, it'll hit this. and then that will allow fluid to go to close the gear doors. Okay. And it uses the big key here with sequence valve is it uses these actuators physically pressing something in order to do it. Compared to a priority valves use pressure. So remember, when things are moving, the pressure actually drops, right? When we allow flow to happen, the pressure is going to drop. And so what happens here in this scenario, we've got pressure going from our pressure manifold, and we want to open our gear doors first. Well, while the gear doors are opening, while this upper actuator is moving to the right, there will be a drop in system pressure because it's moving. Once it stops moving, that pressure will ramp back up, and then it'll be high enough to overcome this priority valve, and only once that pressure ramps back up does the priority valve allow flow to come down here to drive the gear down. So sequence valves use mechanical things bumping into the valve or bumping into levers. Priority valves rely on pressure in the system. So remember, pressure, priority, okay? You guys get tested on this at the final? Priority and pressure. Sequence valves are all mechanical. In some instances, we need a split flow. Example would be landing gear in this case. If we want things to move together or we want to ensure equal distribution of flow, we'll have an equalizer valve. And this doesn't show the mechanics inside of it, but essentially you have something that it looks at flow, it looks at pressure on both sides, and there's kind of a shuttle valve that can move back and forth in there. How many of you have been taken a shower in an old house, someone flushed a toilet and you got nailed with hot water? Okay. How many of you have noticed that doesn't happen anymore? That's a flow equalizer valve that you have in. So what happens there, someone flushes the toilet, the cold water gets reduced, right? Now instead of all the cold water going to the shower, it goes to the toilet. But you still have all that hot water coming in. That's why the shower gets hot. They've put new showers have to have one of these flow equalizers in, so it senses, same thing happens. When it senses that drop in cold water flow, it also automatically cuts back on the amount of hot water. And that's why you don't get those hot spikes anymore. This does the same thing with hydraulics. Yeah. Related to shower. It's off topic, but it's something that a lot of you have probably experienced. But it's less and less common with the new style, the shower valves that have been put in the last 20 to 30 years. But if you're in a really old, like I know some of the old off-campus apartments and stuff have some really, really old stuff.